The first topic in this lesson is linearization, and first we're going to talk about a few definitions, the first of which is actually what is linearization. So here it is. If f is a differentiable function at x equals a, then the approximating function L of x equals f of a plus f prime of a times the quantity x minus a is the linearization of f at a. And also, the next definition, the standard linear approximation. This approximation, f of x equals L of x of f by L, is the standard linear approximation of f at a. The point x equals a is the center of approximation. And really, I just want to make sure that you understand that x is the variable here. A is some specific value. It's kind of like c we were using earlier. The book has insisted on using a. The book that I'm using has insisted on using a for its variable. But you just think of it through all of the limit and early derivative lessons. C being a constant, but c was that specific value of x. It's the same thing right here. A is just a specific value of x. Let's take a look at what all this stuff means on the next slide. So here you have a function, this little curve right here. This is f of x, some function. And what ends up happening is you pick a point right here, a comma f of a. So if you drew some little markers down like this, the x value, the specific x value is a, and here is the y value at that point, f of a. And then, say for example, you want to find that tangent line that's right there. This is the tangent line, and that tangent line is f prime of a. That's the slope of that tangent line. So what we ended up doing at that point was saying, if we were being very, very general about it, we would say that y minus y1 equals m times x minus x1. Well, y1, there we go. And you can see that the point that we know is f of a. That's the y value there, so I'm going to substitute that in. So this is y minus f of a equals, the slope of that tangent line is way over here, f prime of a times x minus, and the point that we know, the x value, is a. So if you just add f of a to both sides, you'll see that you'll get the equation exactly of what the linearization is. F of a plus f prime of a times x minus a. So the linearization is strongly related to finding the slope of the tangent line. There are some differences that we will get into a little bit later, but this is something that you pretty much already know how to do. It's just now we don't call this we don't call this y, we call it L of x. And up here in the picture, essentially what that means is that we would say that we name this line that's right here L. So that line is now called L. So this is, again, very, very similar to finding the equation of a tangent line, but it's different, and we'll get to that just a little bit later. So here in this example, we are asked to find the linearization L of x at x equals a. And so that is the direction. You have a function here, f of x equals 3x squared minus 7x minus 11, and we're trying to find the linearization of this function at the centered at, if you want to use the terminology, 8. So the first thing that you'll want to do here is you will want to find the derivative. So we want to find f prime of x. And more specifically, we want to find f prime of 8, but we'll do that in a second. So this is 6x minus 7. And that tells us that f prime of 8 equals 41. So f prime of 8 is 41. There's that. We also need to find out what is f of 8. And when you substitute 8 in for this x and this x, you will get 123. So now that we have all of that, we can start substituting in everything that we know. So L of x equals, what was it? F of a plus f prime of a times x minus a. So we know that the linearization at that particular x value 8 is 123. That is f of 8, right? We would substitute 8 in here and get 123 plus 41. That is the slope when x equals 8 times x minus 8. There is the linearization centered at 8 for the function 3x squared minus 7x minus 11. In this example, we are asked to approximate what f of x will be, or what the y value will be, if the function is the cube root of x at the specific point, or at the specific x value, 26.5. Well, some of you out there watching might say, well, hey, this is really close to 27. I know this, the cube root of 27, the cube root of 27 is 3. So why don't we pick that to be our specific a value? Because that is something that we know. We know the cube root of 27 is 3. In fact, why don't we write that? The cube root of 27 is 3. And that, in fact, is f of a, which will come in handy in just a moment. The next thing you want to do is find f prime of x. And that will end up being 1 over 3x to the 2/3 power. And again, if you tried to find the slope of the tangent line at this point, you still can't do it because you have this 26.5, the cube root of 26.5. We don't know, we're trying to figure that out. This also involves that. So what we do instead is we approximate it at 27, aka f prime of a. So this will be 1 over 3 times 27 to the 2/3 power. And what that gives you here is 1 over 27. So f of a equals 1 over 27. All right, so now we have all of the information we need for linearization. So check this out. We have L of x equals, remember the formula is f of a plus f prime of a times x minus a. And we just set up this function. L of x equals, f of a is, I'm going to circle it up here, 3 plus f prime of a, right here, 1 over 27 times x minus, what did we pick a to be? A was 27. All right, so there is the linearization of the function. How are we going to use that? Well, over here, this is what we were trying to figure out. So if we take this and substitute it in for x here, we will have a very good approximation of what the cube root of 26.5 is. So this is 3 plus 1 over 27 times 26.5 minus 27. Well, this is easy enough. This here is just negative 1/2. That set of parentheses, that's what that reduces to. So then we can multiply 1 over 27 times negative 1/2 and get negative 1 over 54, which means you have 2 and 53/54ths as your approximate answer for 26, the cube root of 26.5. Let's take a look at how close this answer is on the next slide. On the previous slide, we approximated that the cube root of 26.5 is 2 and 53/54ths, or 2 and 53 over 54. If you substituted this number, 26.5, and took the cube root of it in a calculator, you would get something like 9.9813, 6597, something like that. So what we can do then is we can figure out how close we were. Well, we need to now change this over into a decimal just to make it easy enough to compare. So let's see, 53 over 54 gives you 2.981481, and it looks like 481 repeats forever. And you can tell just by looking here that 2.9814, if you round to 4 decimal places, I mean, that's pretty stinking close, but we could do better. I mean, I used a calculator to get this here. I used a calculator to get this one here. I sort of fudged the rounding over here, right? This is really 2.9815, 2.9814, and called it close enough out to 4 decimal places. There has to be a better way to compare or find the error between what we got by linearization and the exact amount. And there is, but before we can do anything with that, I have to introduce differentials. Differentials. So we have a function y equals f of x, and it's a differentiable function. The differential dx is an independent variable, and the differential dy is equal to f prime of x times dx. And you might be looking at this and saying, wow, that looks really stinking familiar to something that I've seen before. If you remember when I was going over the notations for derivatives, we had dy dx and f prime of x. So these are two different ways to represent the derivative. So if you find the derivative of y with respect to x, that's the same thing as finding f prime of x. I mean, it's pretty easy to see at this point. You see, if you multiply both sides by dx, the dx is reduced away here and give you this equation here. So really, dx and dy are variables, and we can manipulate them around equations just like we could any other variable or any other constant. So we will, and this is going to be a very good setup for the next big topic in calculus, called integration. And finding differentials is easier than you might think. Let's take a look at a few examples. Example: you are going to be tasked with finding differentials. And so with this, all you are really doing is finding the derivative of both sides, except you're not going to use the notation dy dx anymore. So what we will end up doing is that you will find dy, and that is equal to 1/2, well, I should say 5/2 by the power rule. 5 times the 1/2 is 5/2, x to the 4th dx. So the dx will be on the right side of the equation when you are trying to find differentials. So you're still going through and finding the derivative, but now there will not be the dy dx over here. The dx is multiplied to the other side of the equation. So when you take a look at this next example, when you find dy, the differential dy, that will be a secant cube root of x tangent cube root of x, because the derivative of secant is secant tangent. And then by the chain rule, you will have all of that multiplied times 1/3 x to the 2/3 power dx. So again, you are just taking the derivative like you normally would. Here you see a function inside of another function that involves chain rule. So you take the derivative of the outside function, secant tangent, leave the inside function alone, and then multiply the derivative of the inside function behind it all. And that's it. You found the differential dy equals all of that. And then in this last one, just to throw it in there, dy will equal, this involves the product rule as well as a chain rule. So we're not out of the dark yet on derivatives. We're very, very close. So here we have the first function times the derivative of the second function, which would be cosine x to the 5th times 5x to the 4th, plus the second function, sine of x to the 5th, times the derivative of the first is 1. All of this multiplied by dx. The entire right side of the equation multiplied by dx. Now I didn't use any parentheses around the 5/2 x to the 4th here, nor did I even use any parentheses around all of this trig stuff here. And that's because that was all one term. Since there was more than one term here, here's one term, here's another, I had to put parentheses around the entire side. If you want to be safe about it, you can put parentheses around the entire side here, and brackets might be better here. We put brackets around the entire right side of this equation and then multiply it by dx. It's a safe move, but it doesn't need to be done unless you have more than one term. On the next slide, I want to find the differential of yet another function, and then explain how that relates with the linearization of a function, maybe to give a little bit of a better insight as to what dy and dx are, and just, why we can separate these. So for this example, finding the differential is relatively easy. You're just taking the derivative of 13x to the fourth power. You'll end up with 52x cubed. And on this side there will be a dx, and on the left side there's a dy. These are the differentials separated out. Great. Well, let's see what happens when we find the linearization at x equals a. So in order to do that, we need to know what the y value is when a is substituted in for x. So let's see, the y value when a is substituted in for x would be, I'm going to call it f of a, just so I can remember, 13a to the fourth. And we need to know what the derivative is with a substituted in for x, and that's over here. So I'm going to call that f prime of a, again, just so I can keep this straight in the example here. This is 52a cubed. But one thing you'll want to keep in mind is that both of these values are numbers. These are both numbers because we picked a specific number to substitute in for x here and here, so we get numbers back. So the linearization then, L of x equals f of a plus f prime of a times x minus a. So if we go through and substitute all of these things in like they are supposed to be, you can see that f prime of a is 52a cubed. So let me at least substitute that in there so we can get that squared away. Equals f of a plus 52a cubed times x minus a. Now in this current form, I only substituted in this derivative here so that I could come back up here to this and get some explanation happening. So one last step here is that you want the linearization to have the f of a subtracted from it, 52a cubed times x minus a. So if you compare this, I'm going to do the left side, the 52a cubed under white and the x minus a here. Those all correspond with these same three parts up here. So you can think of this dy, this differential equation up here, in terms of a linearization in the way that dy is the difference between the linear approximation and the actual value at f of a, and the dx over here, the differential dx, is represented by this small difference in x values down here. Remember, x is the variable or the specific value we want, and a is the approximate one that we were looking at close by. So these dy and dx just end up being very, very small changes in the y variable, or very small changes in the x variable. In this example, you are asked to find delta f. That's the first part of this. And that is defined as finding the function value just a little bit to the right. This should be plus dx. There we go. Just a little bit to the right of the y value you're interested in, and you're just taking a difference in y values there. Then you are asked to find the differential df, which is similar to finding the differential dy, by finding the derivative at a particular x value and then multiplying it by dx, which is given, you can see, and the error between these two, which is given as the absolute value of delta x minus the differential of, delta f minus the differential df. And all of this information will be given to you, f of x, x naught, or again, this could be a, the specific x value, and the differential dx. So now we're going to actually put a number to dx, and let's see what happens. So the first thing we need is we need to figure out what f of 5.01 is. So let's figure that out. F of 5.01 is negative 2 times 5.01 squared plus 5.01. And when you crunch all that out, you'll end up with negative 45.1902. From there, you will want to subtract f of 5. You can see I'm just following what this equation is asking me to do up here. So f of 5 will be negative 2 times 5 squared plus 5, which is negative 45. So when these two are subtracted, so I'm going to take away a negative 45, I will end up with a negative 0.1902. So this is the actual difference between the function when x is 5 and the function when x is 5.01, something close by. That's the actual difference. So what you are asked to figure out next is the difference using the linearization. So when you have this differential df, that is what you use when you don't have an equation defined as y. So here we could say the differential, if it were y equal to negative 2x squared plus x, then we would find dy equals blah blah blah. But since it is not y and is instead f of x, we find the differential df. So it's still done the same way. We just find that the differential df is the derivative of this side, so negative 4x plus 1 times dx. So what that leaves us with is negative 4 times, well, our x naught value over here is 5, so we need to substitute that in for this x. So that ends up being df equals negative 4 times 5 minus 1, and then dx, again up here, dx is 0.01, so times 0.01. Sorry, this is plus 1 here. There we go. So this is negative 19 times 0.01. That is negative 0.19. So using the linearization at that particular point, we know that we should get the answer negative 0.19. the last thing here is to figure out how far off is the linearization from the actual thing. So we take the absolute value of negative 0.1902 and we subtract the differential df, which we computed as negative 0.19, and that equals 0.0002. There's the error we get using the linearization instead of the actual difference in the y values. So linearization can help make these approximations much easier to compute. Go forth and conquer.